Greetings everybody and welcome to CP Physics Series and Parallel Circuits 2.0. The last one I recorded did not have any sound. Bummer. Alright, so we're going to make this one quick. Today we're talking about circuits. There's two types of circuits, series and parallel. We're going to start with the series kind. So in a series circuit, only one path for the current to follow. There is only one path for the current to go on. And along this path there is a user, followed by another user. For example, a resistor followed by a light, or a light followed by a resistor, or a light followed by another light, or a light followed by a toaster. Just all different kinds of users along one path. So here I have a little example. Here's our generator supplying the voltage. Current comes out, goes along this guy. It's going to cross one resistor, the first light bulb, cross the second resistor, and across the third resistor. So all these light bulbs are actually resistors. And they all have different resistances. So how do we find out the total resistance? So across this series circuit, each one of those light bulbs, each one of the users, has the same exact current going across it. The effective resistance, or the equivalent resistance, is the sum of all the resistors in the series. So the equivalent resistance equals the first resistance plus the second resistance plus the third resistance plus however many resistors you have on there. The sum of the voltage drop is equal to the total voltage drop. So the equivalent voltage equals the voltage drop across the first one, plus the voltage across the second resistor, plus the voltage across the third resistor, plus however many you have. And now we have parallel circuits. There are two or more paths for the current to follow. So here I have my generator, and here I have little junction points. The current can go anywhere it wants after the junction point. It can go across this way, or it can start coming down this way. And it's going to hit this junction point. It can go this way, or it can continue on this way. Or it can hit this junction point and go this way, or continue on this way. But eventually it's all just going to come back out here. Rules for the parallel circuits. The total current in the circuit is the sum of the current in all its paths. So each path can have a different current, but the total current, when you add all those up, is going to be equal to whatever current is supplied originally, like through generator, battery, or etc. And this guy should be up here. I think it's okay on your notes. So the equation for this is the total current equals the first current plus the second current plus the third current. So current in each branch, you're going to add them all up to get the total current. The equivalent resistance decreases with more parallel resistors. So the more resistors you add, the resistance actually goes down. And we'll talk about why that is in a second. Like I said, this box should be here, this box should be here. I think it's correct on your notes though. So how we find the equivalent resistance for a parallel circuit, we have this equation. 1 over the equivalent resistance equals 1 over the first, plus 1 over the second, plus 1 over the third resistance, plus 1 over r to the n resistances. So n being however many resistors you have. And the voltage is the same in each path. In series circuits, the current was the same in each path, but in parallel circuits, the voltage is the same in each path. Then along comes this guy named Kirchoff, and he started making some laws, and here's his current law. His current law says that any junction point in an electrical circuit, the total current into the junction equals the total current out of the junction. Basically, what goes in must come out. And a little picture for you. So we have a current on this path, I1, current on the second path, I2. They're going to come into the junction point, and the current coming out is going to be I3. So we simply just add these currents together. I3 is not going to be bigger than I1 plus I2. It's not going to be smaller than I1 plus I2. It's going to be the exact same as I1 plus I2. Because what goes in must come out. He also had a voltage law. And in this voltage law, he says, in any complete path in an electrical circuit, the sum of the voltage increases equals the sum of the voltage drops. And he liked to explain things harder than they had to be. So what this basically says is what goes up must come down. So voltage increases equals the sum of the voltage drops. What goes up must come down. So here we have our battery, which is voltage up, and across each resistor, the voltage goes down. So to find the total voltage, we have the up minus the down minus another down. It's going to be 0. We can also write this as V equals IR1 plus IR2. That's just bringing these guys to the other side to show you that what goes up must go down. So now how about some laws for some series circuits? This page you should refer to when doing problems involving series circuits. So as I said before, the current is the same at all points in the circuit. Each resistor has the same current flowing through it. The total voltage supplied to the circuit is equal to the sum of the voltage drops across the individual loads. I already said this too. So given that our total voltage ups equal our voltage downs, and from Ohm's law knowing that voltage equals IR, we could substitute IR in for all these things. So ITRT equals I1R1 plus I2R2 plus I3R3 plus however many I's that you have. And since it's a series circuit and the current is the same for all resistors, we could just get rid of the subscripts on all the I's, like so. In doing this, we can actually get rid of the I since they're all equal, and we're left with the equivalent resistance, or total resistance, equals the sum of all the resistors in the series. So a quick little example. Here we have a series circuit with 3 resistors. First thing we want to do is find the equivalent resistance. So to do that, we add up the value of all the resistors, 17 plus 12 plus 11, and you get 40. So notice that the equivalent resistance for a series circuit is always larger than any of the other ones, any of the individual resistances. And next we're going to try to find the current, and we know the current equals voltage divided by resistance, so the total current for the whole circuit is going to equal the total voltage divided by the equivalent resistance in 1.5 amps. And since the current is the same over each resistor, all the currents are the same. They're all 1.5 amps. However, the voltage is going to be different. You have to find the voltage across each resistor. So the voltage for this first resistor is going to be the current across the resistor times the resistance of the resistor. So 1.5 amps times 17 ohms, you get 25.5 volts. Do the same for V2, you get 18 volts. And the same for R3, and you get 16.5 volts. And if you add all these guys up together, you do in fact get the total resistance of 60 volts. Moving on to parallel circuits, they're a little different than series. So at a junction, the current out is going to be equal to the sum of all the currents in, or vice versa. So the current can be different on each one of these 3 paths that we have here, X, Y, and Z. But the voltage is the same. So remember that voltage is the same for parallel, current is the same for series. So the total voltage is going to be equal to the voltage on the first path, it's going to equal the voltage on the second path, and voltage on the third path, and yada yada yada. To find the equivalent resistance, we know that the total current equals the sum of all the currents on the paths. And from Ohm's law, we know that I equals V over R. So we plug V over R in wherever we see an I. So total voltage divided by total resistance equals the first voltage divided by the first resistance, and so on and so on. But since it's a parallel circuit, all the voltages are the same, so we can get rid of the subscripts on the V's. They cancel out, and you're left with 1 over the equivalent resistance equals 1 over R1 plus 1 over R2 plus 1 over R yada yada yada. So here's a quick simple little example. All of these resistors are in parallel. They're all equal to 12 ohms. So 1 over 12 plus 1 over 12 plus 1 over 12 gives us 3 over 12. which gives us 1 over RQ equals 0.25 ohms. Now you're not done here. This is 1 over REQ. We need to find REQ. And how we do that is we do 1 divided by whatever this number is. So 1 divided by that guy, and you get an equivalent resistance of 4 ohms. Notice for parallel circuits that the equivalent resistance is less than any of these guys. So adding more resistors is only going to make this go down. Another quick example, find the equivalent resistance. So 1 over 5 plus 1 over 7 plus 1 over 12. You get something that looks like this. But remember, this is not our final answer because this is 1 over REQ. So you have to do 1 divided by this guy to find out what REQ is. And 2.3 ohms. So again, notice much lower than these guys. So what happens if we have a circuit that has both series and parallel components? Well, the first thing you want to do is you want to get rid of the parallel guys. So you want to find the equivalent resistance for this little parallel set right here. So 1 over 4 plus 1 over 4 gives us 2 over 4. Flip that upside down, you get 2 ohms. And replace this guy with just 1 resistor that has the equivalent resistance of 2 ohms and continue on from there. Now it's pretty easy to find the total resistance for the circuit. 2 plus 2 plus 6 is going to give us 10 ohms. So get rid of the parallel guys and then do the series stuff. Pretty simple, and hand in your notes and stuff like you're supposed to do. See you in class.